Hello, this lecture will cover pages 256 through 259 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Digital Arithmetic 6B, 2's complement notation in signed binary numbers. If you remember the last lecture we talked about, we said there was three different types of number systems, signed binary number systems we were going to talk about: signed magnitude, 1's complement, and 2's complement. We discussed signed magnitude, we've discussed 1's complement. Now let's take a close look at the most important out of the three, 2's complement notation. By definition, the 2's complement of a number is equal to the 1's complement plus 1. In other words, you invert the number and you add 1 to it. Therefore, in 2's complement, let's take a look here. Here we have a plus 12. Here we have a plus 25. Here we have a plus 48. Notice that all three are positive numbers. Here's our positive 12. Here's our positive 25, 16, and 9. Here's our positive 48, 32, and 16. We made this comment before, and it's so important I'm going to mention it again. Positive numbers are always represented the same way in all three notations. You can't tell the difference with positive numbers. Where they distinguish themselves is the way you represent the negative number. Here we have a negative 12, and I want to show it in 2's complement notation. So you start with the plus 12. You take the 1's complement of it. There's the 1's complement of plus 12. And you add 1 to that. This number here is the 2's complement form of negative 12. You're not going to be able to look at these numbers. It takes somebody that works with this a lot to be able to look at this and see that that is a negative 12 in 2's complement notation. Now, if you ever get an answer it looks like that and somebody tells you it's 2's complement notation, what you need to do is recognize it's a negative number by putting a 1 there. There's your negative. That 1 means it's a negative number. And then you need to take the 2's complement of that number. You have to invert it and add 1. And you'll get a 12, and then you know that's a negative 12. Let's take a look at down here at a minus 18. Well, start with the plus 18. Take the 1's complement. That's what it says to do. You take the 1's complement and add 1. So we're taking the 1's complement down here, and we're adding 1. And that number right there is negative 18 in 2's complement. If you need to check your work, you know it's a negative number because there's a 1 there. You invert that number and add 1, and you'll get back to here. You'll get 18, and you know it's a negative 18. I'm going to show you a very convenient way of taking the 2's complement of a number. I learned this when I was at Texas Instruments. Matter of fact, one of the engineers showed this to me. Let me take a negative 12. I want to show a negative 12, and I want to show that in 2's complement. Okay. What you can do is you can start with a plus 12. Rather than taking the 1's complement and add 1, you start on the right-hand side and you copy down the digits until you come to the first 1. When you come to the first 1, you write it down, and then you invert everything thereafter. That is a negative 12. If you don't believe me, look back here. There was the negative 12. And here it is. What about that negative 18? Well, the plus 18 looks like this, 16 and 2. There's 16 and 2. So what's a that's a plus 18. What's the 2's complement of that number? You could take the 1's complement and add 1, or you start writing digits down from the right to the left till you get to the first 1. Once you get to that first 1, you write it down, and then you invert everything thereafter. Notice that's an echo echo. Rather than saying 1 1 1 0 1 1 1 0, it's an echo echo. That's how you show a negative 18 in 2's complement. Well, here it is. The echo echo that we did the long way. So keep that in mind. If I give you a number, it looks like this. And I tell you that number right there is a 2's complement number. What does it represent? Well, you know it's a negative number. It's a negative what? We'll take the 2's complement of it. Start writing the numbers down, digits down from the right to the left till you get to the first one, copy it down, and invert everything thereafter. That's a negative 8. That's just a way of showing negative 8 in 2's complement. It takes practice, but it's not difficult. I'll let you use that technique. On page 257, for a 4-bit computer using 2's complement math, I just showed you all the possibilities here from 0, 0, 0, 0 up to 0, 1, 1, 1. That's 8 different states. That's 8 positive numbers because 0 is the first number through plus 7. And then these bottom digits started 0, 0, 0 through 1, 1, 1 with the sign bit being 1. There's 8 negative numbers. So for a 4-bit binary number using 2's complement math, this is the range from -8 up to plus 7. Keep in mind that you're always going to have one short on the positive end because 0 is the first positive number. Here's an equation you'll see in a number of classes, particularly if you do have some programming classes or in your microprocessor class. The range for an n-bit signed number is negative 2 to the n minus 1 is less than or equal to the range, which is less than or equal to plus 2 to the n minus 1 minus 1. That's on the plus side. This works to give you a range for any n-bit number. Here we have a 4-bit number. Up here we had a 4-bit number. What's the range? We'll use this formula to give you the range. It's negative 2 to the third is less than or equal to the range, which is less than or equal to plus 2 to the third minus 1. And I always ask my face-to-face class, why are we subtracting 1 here? And I wait for an answer. On the plus side, why are we always 1 short? Because 0 is the first positive number. And why are we subtracting 1 in the exponent? Because you have to strip off the sign bit. You're just stripping off the sign bit. Because it's not going to give you any weight. So I think for homework, I'm going to ask you, what's the range for 8-bit? What's the range for an 8-bit 2's complement number? It's not double this. It's not just 2 times this. It's negative 2 to the 7th is less than or equal to the range, which is less than or equal to plus 2 to the 7th minus 1. It's minus 256 is less than or equal to the range, which is less than or equal to, matter of fact, that's not right. It's negative 128 is less than or equal to the range, which is less than or equal to plus 127 if it's an 8-bit number. A 16-bit number is negative 32,000 something to plus 32,000 something. Make sure you get that. Make sure you have that down in the homework. You're going to see that on an exam. This is an important formula. It's the range of an n-bit signed number. I gave you answers here, but I want you to work these out. Make sure you can see how I got what is the range of a 2's complement number if n is 8 bits. What's the range of a 2's complement number if n is equal to 16 bits? By the way, that's called double precision. And some students ask me, well, if you have 16 bits and go to double precision to extend your range? Where's your sign bit? Is it here and here? No, no. This is the sign bit. That's the sign bit. You don't have two sign bits. Look number 3 over. What is the range of a 2's complement number if n equals 64 bits? By the way, this is called double precision for 32 bits. This is double precision for 8 bits up here. I want you to see examples 6.3, 6.4, and 6.5 on page 317. Not sure what textbook we're looking at, but let me see. Let me show you what they look like. I'll use this textbook here, and let's see what they look like here. Somewhere in your book, I want you to find these examples. 6.3, make sure you understand that example. 6.4, make sure you understand that example. And 6.5, make sure you understand that example. On page 259, we're going to do some problems here, just a couple problems. You're going to have to do this for homework, and you're definitely going to have to do this on the exam. I don't think I'm going to spend any time giving you 1's complement math examples. That was just a building block to get to where we're at here. But I'm definitely going to hold you responsible for understanding 2's complement math. So if you take a look here, I just did 4 examples, and I want you to work out some examples on your own. And I want to show you that 2's complement math always works. That's why when you read about different microprocessor chips, it'll always tell you in their specifications it uses 2's complement arithmetic in its algorithms. What does that mean? Well, keep in mind this is all 2's complement now. You have to think strictly 2's complement. Here's a +7. Well, they're all positive numbers are shown the same way no matter what notation. But how do you show a -7? How do you show a -7? You can't just look at that and see that. What you have to do to show a -7 before you put it on your paper is do some chicken scratching. I'm going to take an extra sheet of paper and show you what I mean. Well, I don't have to, because here's a +7. How do I get a -7? You first write down the +7, and then you take the 2's complement of that. That'll give you the -7. You can do the 1's complement +1, but I just start at the right. Write down bits till you get to the first one. Well, the first one's there. Put down the 1, and you invert everything from that point on. There is your -7. When you add these up, you should get 0. Add these 2 up, and you get 0. But you get a carry out here. You always ignore the carry bit in 2's complement notation. So on your exam, I want to see you do this. Put an X through it and write the word ignore. To get full credit, you have to do that. I can't tell you how many times earlier in my career, and this happened more than once, where I was at an interview. I can remember down in Baltimore, I was at an interview, and the engineering manager, quote, "Skip, what do you do with the carry in 2's complement arithmetic?" And I said, "Ignore it." He said, "That's right. That's what I want you to say." Here's a +12, here's a -12. I'll keep these for the same for now, just so it's easy to get the 2's complement here. That's the only reason I'm keeping these the same. I'm going to change them down here. But here's a +12. Okay, you shouldn't have any trouble with that. You have to show a -12. It's just a 2's complement of this number. Start writing digits down until you get to the first one, copy it down, then you invert everything thereafter. Add this and this. You get back to 0. The answer is 0. You get a carry out here from the 8th bit, but you always ignore carry. You always ignore the carry in 2's complement notation. Here you have a plus 16 and a minus 12. There's your plus 16. What about a minus 12? Well, you have to write on a piece of paper a plus 12 somewhere. So write down a plus 12 using 8 bits, and then get the 2's complement of that number. I'll do one more. Here's a plus 12. And that's a plus 12. I want a negative 12 in 2's complement. So rather than taking the 1's complement and adding 1, it takes too much time. I copy down digits till I get to the first 1. Write down that first 1, and then invert everything thereafter. It's a Fox 4. It's a Fox 4. And then you add them up. It's just to add addition at that point. See if you get 4. You get 4. There's your answer. Works every time. You ignore the carry. Sometimes you don't get a carry, but if you do, you ignore it. Down here you have a minus 10 and a minus 15. There's your minus 10. Make sure you can see that. If you don't see this and you can't do it quickly, you're going to miss it on the test. Here's a minus 10 in 2's complement. Here's a minus 15 in 2's complement. What I want you to do is add them up. You get a 1, 1, 1, 0, 0, 1, 1, 1 with a carry. You ignore the carry. Now you have to interpret that. Don't be like some people when you're working these problems out and you get the positive number and you take the 2's complement. Just because I'm saying it's a 2's complement problem, you don't have to take the 2's complement. If the answer is positive, that's the answer. Here you're going to have to take the 2's complement of that to check your work, because it's a negative number. No, if you just want to circle that and say that's a negative 25 and be done with it, you might be right and you might get it right. But I would check your work. How would you check your work if that's a 2's complement number? Listen carefully to what I'm saying. You don't take the 2's complement of the answer. If it's a positive answer, that's the answer. You only have to take the 2's complement if it's a negative solution, negative answer, to interpret it. I know this is a negative number, so I know there's a negative there. But it's a negative what? Take the 2's complement of that number. Write it down. The 1, the 0, the 0, the 1, the 1, the 0, 0, 0. And you'll get a 25. And that tells you it's a negative 25. But that's what you circle because that's the answer. A very important note. You always ignore the final carry bit when using 2's complement notation because it has no practical value. Now, what I would do to prepare for the exam or the quiz is I would just take some numbers. I would take a plus 42 and a minus 16 and do it in 2's complement and see if you get the answer. See if you get this answer. Take a minus 12 and a minus 30 and see if you get your minus 42. 2's complement numbers and interpret it and see if it's a minus 42. Write down 3 or 4 of these. Make them up. You don't have to go up in 156 minus 122. We don't have to worry about that. Just make sure you understand 2's complement notation. Because when we look at the hardware through the next couple lectures, you're going to see that the way that the mathematics is done is with 2's complement arithmetic, and they do that 2's complement arithmetic with hardware. It's very easy to do with hardware, and I'm going to show you that in the next lecture. That concludes this lecture.